Now let's look at another very important concept, which is known as a spectral radius of a matrix. So initially let's try to define what is a spectral norm. Sorry, so the spectral radius. Not that this is different from the spectral norm. Don't confuse. The spectral radius is normally denoted as rho of A of a matrix. Matrix A, which belongs to Cn cross N, is rho of A is defined as the maximum modulus of lambda, where lambda is an eigenvalue of A. So we have not formally discussed what eigenvalues and eigenvectors are, but a very introductory definition can be if A is a matrix, and for some vector x, if it gives lambda times x, which is basically scaling of this vector, then this lambda is known as the eigenvalue, and this x is known as the eigenvector. This is anyway. It is discussed in detail. It will be discussed in detail in the coming lectures. So if there is an eigenvalue, then this is a spectral norm. But spectral norm has a very important property that it lower bounds the norm of a matrix. In fact, spectral norm is the closest lower bound which you can find. It's the largest lower bound which you can find for the matrix norm, or matrix A. Okay. So how do we prove this? So what I mean is the theorem says norm of A is always greater than or equal to rho of A. So take any, this is valid for any matrix A and valid for any matrix A and any norm. Wait, not that these are any matrix in the sense these are square matrices. Any square matrix, it's independent of the norm and it's independent of the matrix. So how do we prove this? Prove this. If lambda is the eigenvalue of A, implies mod of lambda is always less than or equal to rho of A. This is true, right? Why this is true? Because this is the largest modulus, largest eigenvalue, largest magnitude of the eigenvalue. So all other, so also note that here lambda can be anything, real, imaginary, complex, whatever. But we can find the modulus of a complex number as well. Fine. Yeah. So this is true, and the x is at least one eigenvector corresponding to eigenvalue with magnitude rho of A. Okay, this is, in fact, rho of A is actually, rho of A is equal to modulus of lambda max. Oh, it's not exactly modulus of lambda max. If it's complex, then you can't initially compare. Okay, it's actually max of modulus of lambda. Fine. We've already, I mean, let's not go in that detail. Fine. This is true, and there should be at least one eigenvector. This is true for all matrices. Even if you have repeated eigenvalues, then there should be at least one eigenvector corresponding to distinct eigenvalues. Fine. Now, consider we know AX is equal to lambda x, right? Because it's a for all x not equal to 0. And we've chosen the x such that uh, so the x here, so we're considering this case, the case where a lambda is equal to a mod of lambda is equal to rho r, which is like the modulus of this gives the maximum uh, the spectral radius, and x be its corresponding eigenvector. Okay, so we have lambda. I think it's better to write something like lambda dash. We have many eigenvectors, and lambda dash is the one which gives this, and x is the corresponding. So this lambda dash and x is an eigenvalue, eigenvector pair. Eigenvalue, eigenvector pair. Okay. So now let's make a matrix x crypt x by stacking all these eigenvectors along the columns. Right? And this will be a T cross n matrix. Right? Such that we stack n eigenvectors, I mean, these eigenx n times along the columns of this matrix. And we know A into x is equal to lambda times x. Why? Because x is an eigenvector. So every time you multiply A with x, one of these columns, the resultant is lambda x. In fact, it's lambda dash x in this case. Okay, it's lambda dash x. Fine. So if this function is a matrix norm, let's take the matrix norm of this matrix norm. Ax is equal to the matrix norm of lambda dash x. We can actually apply homogeneity here, which is modulus of lambda dash of x. Right? So on the left side, what we have is lambda dash matrix norm of x. But by submultiplicativity, this is equal to norm of ax, right? And just rewriting it, changing the order. But by submultiplicativity, this is less than equal to norm of a into norm of x, right? But we can cancel out matrix norm of x and matrix norm of x on both sides. Why? Because matrix norm of x is not equal to 0 because x is not equal to 0. So we get lambda dash is less than or equal to. So for any, okay, so this lambda, what is this, the modulus of lambda dash? This is rho of a. Rho of a is less than or equal to matrix norm of a. So rho, what this means is, okay, if the result here is, if this is a matrix norm And if n cross n, then just rewriting it for clarity. Rho of A is always less than or equal to norm of A. But there's one thing to note. Rho of A is not a matrix norm. Spectral radius is not a matrix norm. Or it's not even a vector norm on C n squared. We've seen this, like any matrix, you can stack it up as a single column of n square number of terms, and you can take any vector norm. But if you define rho of A as it doesn't even, it's not a matrix norm, it doesn't even satisfy the properties of what do you call it? Not even all first three properties in till triangle inequality. Okay, let's end this discussion here.